In the beginning, there was light. It became the measure of all things, the silent constant, the universal law written into the bones of reality. Nothing could outrun it. Nothing could defy its reign. For over a century, this truth has been our compass, that light defines the speed limit of the cosmos, the unbreakable wall at the edge of possibility. Yet beyond the spirals of galaxies, deeper than the horizon of black holes, there are whispers of places where even this most sacred law falters. Places where light is not merely trapped, but unmade, erased as though it had never been. A void so absolute, so hungry, that it swallows more than photons. It consumes the very geometry of space-time itself, devouring the fabric of reality at a pace faster than the universe should allow. Scientists call them voids, cold regions of darkness scattered across the cosmic web. They appear as absences, great gulfs between the shining threads of galaxies. But the silence they hold is more than emptiness. Instruments strain to explain them, yet their signals suggest something far stranger than absence, a devouring. Imagine a place where the speed of light is no longer protection, where the bedrock of physics crumbles, and where the rules that once defined reality dissolve into shadow. If light itself can be swallowed, what hope does matter have? What hope does memory, or time, or existence itself? And so the question lingers, suspended in the silence. What happens when reality allows something faster than physics allows? At the dawn of the 20th century, physics stood at a precipice. The Newtonian clockwork universe, predictable, precise, and bound by the equations of motion, had carried humanity through centuries of discovery. Yet, as telescopes grew stronger and mathematics cut deeper into the fabric of reality, small cracks began to appear in that clockwork. Starlight bent where it should not. The orbits of planets whispered of hidden hands, and the very nature of space and time seemed less like a stage and more like a participant in the drama of existence. Into this uncertainty stepped Albert Einstein. In 1905 and later in 1915, his work on relativity rewrote the laws of the cosmos. No longer was space a passive emptiness, it was a living fabric, warped and curved by matter and energy. And within that framework, light, the speed of photons, became the ultimate constant, the great unbreakable limit. Nothing could travel faster. No force could exceed it. Light itself became the ruler by which reality was measured. But within Einstein's equations lurked a possibility so strange that even he hesitated to believe it. The mathematics suggested that when matter collapsed beyond a critical point, it would drag space-time down with it, forming a prison from which nothing, not even light, could escape. A singularity, wrapped in an event horizon, silent and invisible. Einstein dismissed them as pathological, a curiosity of equations, unlikely to exist in nature. Yet decades later, others dared to take the mathematics seriously. John Wheeler, the American physicist who gave these monsters their name, black holes, saw them not as mathematical quirks, but as inevitable. If stars live, then they must also die, and in their death throes, they could collapse into these wells of gravity, bottomless and merciless. The event horizon became a boundary, a line in space-time where escape velocity exceeded the speed of light. Beyond it, reality turned inward, swallowed by its own geometry. For years, black holes were theory, ghostly possibilities haunting physics. But in the mid-20th century, the universe began to whisper of their reality. Astronomers found strange X-ray sources flickering in the heavens, objects that shone with the energy of matter being torn apart as it spiraled into darkness. Quasars, brilliant beacons at the edge of the observable universe, blazed with a light so intense that only supermassive black holes could power them. One by one, the pieces of evidence mounted, until denial became impossible. The monsters were real. Yet even as black holes stepped from theory into observation, a deeper unease grew. These entities, predicted by relativity, carried with them paradoxes that gnawed at the heart of physics. If nothing could escape them, what became of the information that fell inside? Stephen Hawking, pushing Einstein's equations against the raw quantum world, revealed that black holes could not remain silent forever. They radiated, slowly evaporating over unimaginable timescales. But if they evaporated completely, then all the information they had swallowed would vanish with them, violating the most sacred law of quantum mechanics. The paradox was not simply academic. It suggested that our understanding of reality was fundamentally incomplete. And then came the voids. By the turn of the 21st century, new instruments lifted our vision beyond individual black holes into the grand structure of the universe itself. Telescopes mapping the cosmic microwave background revealed an intricate web filaments of galaxies stretching across billions of light years, threaded like veins through the cosmos. Between those filaments lay vast regions of emptiness, cosmic voids. They were expected, natural consequences of cosmic evolution. But some were stranger than anticipated. The cold spot in the microwave background, a vast region of unusual emptiness, drew particular attention. Stretching hundreds of millions of light years across, it seemed too large, too empty to be explained by conventional structure formation. If it were simply a statistical fluke, it was an improbably vast one. Other voids, scattered through deep galaxy surveys, carried the same unsettling silence. At first, astronomers thought of them as deserts, empty stretches of cosmic wilderness where galaxies simply never formed. But as instruments grew more precise, whispers of something more began to emerge. Light passing through or near these voids did not behave as expected. Some galaxies appeared dimmer, their photons stretched and smeared in ways not entirely consistent with gravitational lensing alone. Signals bent, weakened, or simply failed to appear. It was as if the voids were not merely empty, but active, swallowing light itself. This suggestion was almost unthinkable. Black holes already challenged the imagination, but at least they were contained singular points, boundaries drawn by event horizons. A void, however, was not a boundary, but a region of space, vast beyond comprehension. If such a region were actively erasing light faster than physics allowed, it would mean that the very geometry of space-time was breaking its own rules. The instruments that uncovered these hints were as varied as they were ingenious. Gravitational wave detectors, sensitive to the ripples of colliding black holes, occasionally registered anomalies, subtle irregularities that hinted at space-time disturbances unaccounted for by known events. X-ray telescopes cataloged mysterious fluctuations in brightness, regions of the sky where radiation dimmed inexplicably, and deep sky surveys revealed missing galaxies not destroyed, but hidden, as though their light had been swallowed on its journey to us. Among those who wrestled with this mystery, awe and fear mingled in equal measure. Had humanity glimpsed structures larger than galaxies, larger than clusters, operating on principles outside the known laws of physics? Or were these simply the scars of processes still misunderstood, echoes of dark matter, or the fingerprints of dark energy at work? The paradox remained. Black holes consume light because gravity bends space-time to infinity. But these voids did not announce themselves with singularities, nor with event horizons. They were not compact prisons, but sprawling abysses. If they were consuming light faster than relativity allowed, then either relativity was incomplete, or the universe itself contained mechanisms stranger than even Einstein had dared to imagine. It was here, in this uneasy silence, that the suspicion arose. Perhaps these voids were not empty at all. Perhaps they were not deserts, but predators consuming not just light, but the very framework of physics. The suspicion that voids might be active rather than passive drove astrophysics into unfamiliar territory. For a century, relativity had been the unshakable guide, declaring the speed of light not merely as a fast-moving traveler, but as a barrier, a wall written into the foundation of reality. To speak of regions where that law faltered was to question the architecture of the cosmos itself. And yet, the evidence refused to be silenced. The first great trigger came not from the eye, but from the ear. The new ears of physics, tuned to the tremors of space-time. Gravitational wave observatories, such as LIGO and Virgo, recorded the faint shivers of colliding black holes. Each detection matched the predictions of relativity with uncanny precision, as if Einstein's equations had leapt from chalkboards into the sky. But hidden among these triumphs were signals that whispered anomalies, distortions, and irregularities not fully explained by black holes alone. These whispers pointed not to compact singularities, but to vast regions of altered space-time, where energy seemed to vanish faster than it should, as though light itself were dissolving before escape. X-ray telescopes added to the unease. Designed to detect the violent radiation of matter torn apart near black holes, they occasionally mapped blank patches where radiation should have been. Stars disappeared from surveys, not through death, but through absence, as though their light had never completed the journey. Gamma-ray bursts, some of the brightest explosions in the universe, sometimes dimmed inexplicably when crossing these regions, like candles smothered by invisible hands. Astronomers resisted the most extreme interpretation. Could these voids really be devouring light faster than escape velocity? Faster than physics permitted? Perhaps not. Perhaps they were filled with dark matter, bending light away. Or perhaps vast concentrations of dark energy, accelerating the expansion of space, stretched photons into invisibility. But the shapes, the patterns, the peculiar silences persisted. As theory struggled, the giants of 20th century physics loomed over the debate. Einstein's general relativity had predicted the inevitability of collapse, but Einstein himself had been cautious. He never truly believed nature would permit the raw infinities his equations suggested. John Wheeler, however, had embraced the strangeness, coining phrases that captured imagination as much as science. Black holes, wormholes, geons. He encouraged a new generation to push against the limits of physics, to explore what space-time might do under pressure. And then came Stephen Hawking, whose work on black hole evaporation revealed not only that black holes might not be eternal, but that their very existence posed contradictions between quantum mechanics and relativity. Each of these figures had glimpsed a deeper fracture, a place where the smooth fabric of physics might unravel. Black holes became laboratories of paradox, where information vanished, time slowed, and the arrow of causality bent under its own weight. But voids threatened to escalate the fracture into something larger, stranger, and more terrifying. Unlike black holes, voids had no centers, no compact cores of collapse. They were not small, but vast. extending for hundreds of millions of light years. If they behaved as anomalies of space-time itself, then they suggested something operating not locally, but cosmically. If black holes were the cracks in reality's glass, voids were entire panes shattering in silence. The awe among scientists was palpable. To confront such mysteries was to stand at the edge of comprehension, staring not into chaos, but into a deeper order that remained veiled. Observatories widened their gaze. The Sloan Digital Sky Survey traced galaxies across the heavens, sketching the cosmic web in exquisite detail. What they found only deepened the strangeness. Immense regions nearly devoid of galaxies, shaped not randomly, but with coherence, as though following rules hidden beneath the known laws. Some researchers speculated that these voids might be linked to the universe's accelerating expansion, first revealed in the late 1990s. The discovery of dark energy had already overturned expectations, showing that space itself was stretching faster and faster. Could voids be focal points of this expansion? Places where dark energy pooled or surged, swallowing light in the process? If so, they were not passive deserts, but engines reshaping the cosmos from within. Others leaned toward quantum explanations. In the seething foam of space-time at its smallest scales, virtual particles flicker into and out of existence. If regions of the vacuum could destabilize, falling into a false vacuum state, they might create expanding bubbles of altered reality. These bubbles, in theory, could propagate faster than light, rewriting space-time as they grew. Though purely speculative, such models whispered unsettling possibilities. That voids might be scars of such processes, remnants of a universe constantly on the verge of self-renewal, erasing itself faster than its own laws should allow. Every new telescope sharpened the enigma. The Planck satellite, mapping the cosmic microwave background with unprecedented clarity, confirmed anomalies like the cold spot too large, too coherent to dismiss as chance. The James Webb Space Telescope, peering deeper into the early universe, revealed galaxies forming where none should be and gaps wider than simulations predicted. Each discovery pulled the thread tighter, unraveling the certainty that physics as we know it was complete. And yet, the deeper the voids were studied, the more they seemed to defy singular explanation. They were neither entirely gravitational nor entirely quantum. They could not be fully dismissed as illusions of dark matter or statistical noise. They existed at the boundary, where mathematics trembled and observation whispered. The awe this inspired was not the awe of triumph, but the awe of humility. Humanity, armed with its equations and machines, had reached the edges of comprehension. Beyond lay regions of silence so profound that even light could not testify to what occurred there. In the quiet of these cosmic gulfs, the question grew heavy. Were the voids glimpses of a deeper order or warnings of an approaching fracture? If light could be swallowed faster than physics allowed, then reality itself might be more fragile than imagined. Perhaps the universe was not a single unbroken fabric, but a patchwork, fraying at its edges, unraveling under forces beyond its own laws. And so, Chapter 1 closed on a note of trembling awe. From Einstein's reluctant equations to Wheeler's daring language, from Hawking's paradoxes to the surveys of modern telescopes, the path had led here to the suspicion that the voids were not empty, that they were alive in a way physics had not yet dared to define, that they might be consuming not just light, but the very certainty that reality could ever be fully known. The revelation struck like thunder across the world of physics. The voids were not behaving as they should. For generations, Scientists had believed that relativity set the ultimate guardrail on reality. Einstein's speed of light was more than a number. It was the unyielding boundary of causality, the line beyond which no particle, no signal, and no force could pass. To even imagine something outrunning light was to imagine a violation of time itself, a collapse of the very structure that held cause and effect together. Yet now, the data whispered of something more unnerving. There were signs faint, scattered, but persistent that within certain vast cosmic voids, photons vanished not by obstruction, not by absorption, but by erasure. If light could not endure the journey, if it seemed to vanish more quickly than relativity permitted, then either the measurements were flawed or reality was bending under a deeper law. For many physicists, the first response was disbelief. Science thrives on skepticism, and extraordinary claims demand extraordinary proof. Surely, they argued, the voids were statistical illusions. Galaxies do not distribute evenly after all. Cosmic chance could easily produce regions that appeared emptier than expected. Or perhaps dust and plasma clouds along the line of sight were dimming the light in subtle ways. Some even suggested that dark matter, that invisible scaffolding upon which galaxies are strung, might bend or scatter photons in ways not yet fully understood. But as instruments sharpened, these simple explanations began to fail. When the Sloan Digital Sky Survey mapped hundreds of thousands of galaxies, the voids appeared too coherent, too structured to be dismissed as chance. When X-ray and gamma-ray observatories tracked photons across billions of light-years, the missing energy was too precise to be written off as dust. Again and again, data from unrelated instruments converged, hinting at the same unsettling pattern. Light itself was being erased, as if swallowed by some process faster than the universe should allow. This was the scientific shock, not merely that the universe was strange, but that it was strange in a way that undercut physics at its root. For a century, relativity had guided cosmology with unflinching accuracy. It had predicted black holes, gravitational waves, and the bending of light by massive bodies, all confirmed with stunning precision. But if the voids were truly consuming light beyond relativity's limits, then Einstein's masterpiece, the bedrock of modern physics, might no longer be sufficient. The implications were staggering. If light was not inviolable, then causality itself, the principle that causes precede effects, might be vulnerable. In relativity, faster-than-light motion leads to paradox, an effect arriving before its cause, time collapsing into loops, reality devouring its own chronology. To confront such possibilities in observation was to stare into the collapse of the universe's logical order. For Stephen Hawking, who had already wrestled with paradoxes in black hole evaporation, such possibilities were not entirely new. His information paradox had revealed that black holes seemed to destroy quantum information, violating quantum theory's most sacred rule. But even Hawking's paradox was confined to the event horizons of collapsed stars. The voids, by contrast, stretched across millions of light-years. If their behavior suggested violations of physics, those violations were not local quirks. They were cosmic in scale. To many in the community, this was not only shocking, but deeply frightening. Science had learned to live with mysteries: dark matter, dark energy, inflation, the quantum vacuum. These were puzzles waiting to be solved. But a phenomenon that actively contradicted relativity itself, this was not a puzzle, but a threat to the very coherence of physics. The fear spread into philosophy as well. Since the days of Newton, Science had been grounded on the assumption that nature's laws were universal, consistent, and unbreakable. If relativity could fracture, if the speed of light could falter, then perhaps the universe was not governed by eternal laws at all, but by shifting, unstable rules. Perhaps physics was not the language of reality, but only the approximation of a deeper order we had not yet touched. Yet the strangest element of this shock was how quiet it was. The voids made no sound, no spectacle. Unlike supernovae that blaze across galaxies or quasars that shine with unimaginable power, the voids announced themselves with silence. Their power lay not in what they produced, but in what they erased. And that silence was, in its way, more terrifying than fire. As the evidence spread, debates ignited. Were these voids simply exaggerations of dark energy's influence, accelerating space to the point that photons were stretched into invisibility? Or were they signatures of exotic physics tachyon-like particles, faster-than-light instabilities lurking within spacetime? Some even whispered of false vacuum decay, bubbles of altered reality expanding within the cosmos, consuming everything they touched at speeds beyond light. Though no evidence confirmed such catastrophic ideas, the parallels were impossible to ignore. The shock was not only scientific, but human. For generations, humanity had taken comfort in the idea that the universe was comprehensible, that equations could chart its behavior, that nature's laws were eternal. Now, as scientists stared into the dark gulfs of the cosmic web, they found themselves asking a darker question. What if the laws themselves were temporary? What if the universe was not bound by permanence, but by instability, by collapse, by rules that could dissolve without warning? The voids became more than empty spaces. They became symbols of uncertainty, places where physics faltered, where human comprehension trembled. They were reminders that the cosmos was not built for us, not designed to be legible. The silence between galaxies was not a canvas waiting to be filled with knowledge. It was a warning that reality, at its deepest level, might not care for our need for coherence. And yet, the shock did more than terrify. It ignited curiosity. For every physicist who resisted, others felt the pull of wonder. What if these voids were the first hints of a deeper law, a grander theory that surpassed relativity and quantum mechanics alike? What if, in the silence, the universe was whispering its secrets, offering a glimpse of the machinery behind existence? This duality, fear and awe, despair and wonder, defined the moment of scientific shock. The voids stood as mirrors, reflecting both the fragility of human knowledge and the vastness of what remained to be discovered. The whispers of anomalies grew into conversations, and the conversations into debates that split across the halls of universities, conferences, and research papers. What had begun as faint signals from telescopes became a philosophical earthquake. If light could vanish more quickly than relativity allowed, then the universe was telling us that the framework we had trusted for over a century was incomplete. Some scientists clung to the hope that the mystery was an artifact of measurement. Instruments, after all, have limits. A flicker in a detector, a calibration error, a subtle effect of intergalactic dust. Such explanations had saved cosmology from embarrassment in the past. But with each new generation of instruments, the excuses became thinner. The James Webb Space Telescope, with its piercing infrared eyes, stripped away the confusion of dust and revealed the same strange patterns. Photons seemed to disappear across distances too short, their absence too consistent, as if something deeper than error was at play. The unsettling nature of the voids lay in their scale. Black holes, for all their strangeness, were small compared to the cosmos. They were extreme, yes, but they were isolated. Voids, on the other hand, sprawled across hundreds of millions of light years. If their behavior pointed to faster-than-light erasure, then the phenomenon was not local, but cosmic in its reach. The implication was devastating. This was not an exotic corner of reality misbehaving, but reality itself shifting on its grandest scales. The shock waves rippled through the philosophy of science. Relativity had already bent human intuition. Time dilated, simultaneity fractured, space curved. Yet it had held firm, offering a universe governed by precise laws. To imagine those laws dissolving in silence was to imagine existence without anchor. Was physics not a description of reality, but merely an approximation, fragile and temporary? Could the universe change its rules midstream, rewriting the conditions of its own existence? The human response was layered. Some physicists spoke cautiously, unwilling to risk careers on claims that smelled of science fiction. Others embraced the shock as an opportunity. For them, the voids were not threats but invitations, glimpses of a new order beyond the horizon of known theory. The dichotomy mirrored the history of science itself: skepticism battling wonder, doubt clashing with imagination. At the center of the debate was causality. Faster-than-light behavior has always carried with it a deeper terror, time itself unraveling. If a signal could outrun light, then in some reference frames, it could arrive before it left, reversing cause and effect. This was more than paradox. It was the collapse of chronology. To many, the voids hinted at just such a fracture, a place where the future devoured the present, where the arrow of time bent back upon itself. It was here that echoes of past paradoxes returned with new force. Hawking's information paradox, long debated in the context of black holes, suddenly seemed less contained. If black holes threatened to erase quantum information, perhaps the voids were showing the same erasure on scales far larger. Could these gulfs in the cosmic web be the universe's way of scattering information itself? A kind of cosmic censorship far stranger than the versions Wheeler once imagined. Observatories began to design tests, seeking ways to tease the truth from silence. If voids consumed light beyond expectation, could gravitational waves crossing those regions also weaken or distort? Detectors tuned their algorithms, searching for irregular ripples, mismatches between predicted and observed signals. Some results hinted at anomalies, though none were conclusive. The data was fragile, balanced at the edge of noise, yet even those fragile hints kept the shock alive. The shock was not confined to the ivory towers of academia. The public, too, felt the tremor. Popular science articles speculated about regions of space where light could not survive, where the laws of physics collapsed. Documentaries whispered of cosmic erasers, places where reality faltered. Though the language was sensational, the underlying unease was genuine. Humanity had always sought comfort in the constancy of nature's laws. To hear that those laws might fail was to feel the ground shift beneath civilization's feet. Still, amid the fear, there was beauty. The voids, for all their menace, reminded humanity of its place. Here was proof, once again, that the cosmos was larger, stranger, and more intricate than imagination could anticipate. Just as Copernicus had displaced Earth from the center, and Einstein had displaced time from its throne, so too Might the voids be displacing light itself from its crown? Perhaps light was not the ultimate ruler of reality, but only a messenger of deeper laws waiting to be revealed. Scientists began to imagine, could the voids be windows into alternate physics? Regions where hidden dimensions revealed themselves? Could they be scars of ancient events, imprints of cosmic inflation still echoing through space-time? Or could they be evidence of quantum instability, bubbles of false vacuum gnawing silently at the universe's edge? Each speculation was more unsettling than the last, yet each carried with it the exhilaration of possibility. The scientific shock, then, was twofold. It was the realization that relativity might not be the final word, that the universe could, under certain conditions, permit phenomena faster than light. And it was the realization that humanity might be living in a reality far more fragile than imagined, a universe not bound by eternal stability, but by precarious balance, always on the verge of rewriting itself. In the end, what unsettled most was not the idea of light being swallowed. It was the recognition that science itself, the very act of knowing, might have limits written into the cosmos. The voids whispered of mysteries beyond reach, questions that could not be resolved with more data, sharper instruments, or better theories. They suggested that some truths might lie forever beyond the horizon of comprehension, hidden in gulfs where light itself could not survive. And so, as the chapter of discovery closed and the chapter of shock opened, physicists found themselves humbled once again. The universe had shown its hand, not with brilliance, but with silence. A silence that consumed light, a silence that consumed certainty, a silence that asked, with quiet menace, what happens when even the laws of physics are not laws, but fleeting agreements destined to break? When the first hints of anomaly emerged, the instinct of science was not retreat, but pursuit. Discovery, after all, is born not from certainty, but from doubt. If the voids whispered of laws breaking, then instruments would be sharpened until the whispers became undeniable. The late 20th and early 21st centuries became a golden age of watching the sky. Not because answers came easily, but because the questions grew darker, stranger, and irresistible. The investigation began with the most ancient of lights, the cosmic microwave background. This faint radiation, the afterglow of the Big Bang, was mapped in detail by satellites such as COBE, WMAP, and later the Planck Observatory. Its faint ripples carried the fossilized imprint of the early universe, the seeds from which galaxies would grow. And in those maps, patterns of emptiness emerged. There were cold spots, regions where the temperature of the microwave background dipped lower than expected. One of them, vast and coherent, stood out like a scar on the fabric of the cosmos. Statistical fluke, some said. Cosmic variance, others countered. Yet as surveys of galaxies deepened, the scar aligned with a true absence of matter. A supervoid, stretching hundreds of millions of light-years. If it were simply emptiness, its presence would be remarkable enough. But when photons passed through it, they arrived weaker than models predicted, as though energy had drained away during their journey. This was not mere emptiness. It was activity. It was erasure. The Hubble Space Telescope, though designed for galaxies and nebulae, contributed in its own way. Its surveys revealed gravitational lensing across vast structures, galaxies bent and magnified by invisible matter. Yet in the direction of certain voids, lensing appeared inconsistent. Galaxies shimmered faintly at the edges of perception, as though their light had been stretched thinner than space-time alone should allow. Hubble, in its precision, whispered that the voids bent light in ways beyond gravity. Then came the Chandra X-ray Observatory, designed to map the violent universe. The coronae of stars, the jets of quasars, the searing heat of galaxy clusters. X-rays are photons of tremendous energy, piercing through dust and gas. They should have been immune to most distortions of the intergalactic medium. Yet even they dimmed when passing through some of the great voids. If ordinary photons could be scattered or absorbed, why should X-rays vanish as well? Their silence was perhaps the most chilling, for it suggested that no light, no matter how energetic, was safe. But it was the arrival of gravitational wave astronomy that deepened the investigation further still. When LIGO and Virgo began to capture the faint ripples of colliding black holes, they confirmed relativity with exquisite precision. Each chirp matched the equations Einstein had left behind. And yet, not all signals were pristine. Some seemed muted, as though the waves had lost part of their strength. A few traveled through regions aligned with known voids. Their shapes subtly altered. The data was thin, perched at the edge of noise, but the implications were profound. Perhaps voids did not only swallow light. Perhaps they consumed space-time ripples themselves. The James Webb Space Telescope, humanity's newest eye on the cosmos, turned its gaze toward galaxies forming in the early universe. What it found unsettled as much as it inspired. Some galaxies shone, where theory said none should exist. Others, expected by simulations, were missing altogether. Between them, gulfs of darkness yawned, larger and stranger than cosmological models could explain. Webb's infrared vision pierced the dust of ancient epochs, but even it could not pierce the silence of the voids. The investigation no longer belonged to astronomy alone. Particle physics entered the fray. Could the voids be the signatures of exotic fields, quantum energies rippling through the vacuum itself? The Large Hadron Collider probed the quantum frontier, searching for clues of hidden dimensions or vacuum instabilities. Though no smoking gun emerged, the absence of easy answers only sharpened the suspicion that the voids belonged to a realm where gravity and quantum mechanics met, a realm science had not yet unified. Patterns began to appear. The voids were not random. They clustered along the cosmic web, aligned with the great filaments that stitched galaxies together. Their shapes were coherent, their boundaries sharper than chaos should allow. This was not noise. This was structure, a structure that science could not yet name. Some investigators proposed that dark energy was the culprit. If the universe is accelerating, perhaps these voids were sites where expansion surged, thinning matter to invisibility and stretching photons until they faded. Others suggested they were scars of inflation, relics of the universe's birth, where bubbles of spacetime had expanded unevenly, leaving behind great wounds in the fabric of the cosmos. A minority whispered of more radical possibilities, domains of alternate physics, regions where the constants of nature themselves differed, bubbles of reality colliding with our own. Every new dataset only deepened the mystery. The Sloan Digital Sky Survey mapped more than 1 million galaxies, tracing the web of structure across billions of light years. Its maps confirmed voids far larger than simulations predicted, voids too vast to form naturally within the known age of the universe. They seemed almost engineered, as if some hidden architect had carved silence into the sky. Of course, no scientist suggested design, but the language of awe was unavoidable. The deeper the investigation went, the more unsettling the question became. Were these voids empty, or were they full of something else? To call them nothing was perhaps the greatest mistake. Nothing does not swallow light. Nothing does not bend gravitational waves. Nothing does not appear as scars on the relic radiation of the Big Bang. Perhaps the voids were not absences at all, but presences of a darker kind, presences invisible to matter and energy, but active, hungry, erasing the very signals by which we know the universe. This was the heart of the investigation. The voids could not be dismissed as simple gaps between galaxies. They were phenomena in their own right, and their silence was not passive. It was active. It was deliberate. The search intensified. Satellites, observatories, and colliders alike were pressed into service. Each returned fragments of truth, shards of a puzzle too large to assemble. And behind every fragment loomed the same chilling possibility. The voids were not places where physics was absent. They were places where physics itself was breaking. The more science pressed against the silence, the more it seemed that the voids were not mistakes, but messages. They were not statistical noise, nor artifacts of faulty detectors. They were signatures of something real, something persistent, something that science had not yet named. And every new line of investigation only tangled the mystery further. Astronomers turned to gravitational lensing, that subtle bending of light by mass, to probe the matter content of voids. Galaxies lying behind these gulfs should appear distorted, their light gently curved by whatever matter, visible or dark, filled the emptiness. But the distortions were weaker than expected. The voids bent light too little, as though mass itself was missing. And yet, paradoxically, photons still vanished when crossing them. If the voids lacked matter, why did they behave like predators, erasing light without the gravity to trap it? Radio astronomy added another layer. The square-kilometer array, still under construction but already partly operational, mapped neutral hydrogen across billions of light-years. These hydrogen clouds, faint and ancient, should trace the scaffolding of the cosmic web. But in the regions aligned with supervoids, the signal thinned more dramatically than models predicted. Hydrogen was not just scarce, it was absent, to a degree that defied formation theories. The voids, it seemed, were not only empty of galaxies, but stripped of the raw ingredients of matter itself. Speculation spread into realms both unsettling and exhilarating. Could these voids be domains of exotic energy, where quantum fluctuations fed on photons and erased them? Some theorists propose the idea of photon decay, a hypothetical process where light particles might not be eternal, but could dissolve into undetectable states under extreme conditions. If so, the voids might be vast laboratories where this hidden law of physics was exposed. Others imagined vacuum instability, bubbles of false vacuum expanding silently, their boundaries consuming photons as they passed. If such processes were real, they would not only rewrite physics, they would threaten the universe itself. For a false vacuum bubble could, in theory, consume everything. The Planck satellite's maps deepened this speculation. The cold spot, already a focus of debate, revealed statistical anomalies too persistent to ignore. Its alignment with a vast supervoid gave rise to whispers that it was no ordinary feature. If the cold spot was evidence of a collision with another universe during cosmic inflation, then perhaps the voids were scars of that same ancient encounter. In that interpretation, they were not simply gaps, but boundaries, places where our universe had brushed against another reality. The James Webb Space Telescope, meanwhile, gazed into these gulfs with its deep infrared vision. Some of its findings were quietly unsettling, faint smudges of galaxies where models predicted none, but more often, absence where galaxies should have been plentiful. The distribution was inconsistent, almost as though the voids followed rules different from the rest of the cosmos. Webb's images, rich in detail, were both maps and questions. They showed not just absence, but a structured absence, a silence that had shape, coherence, and intention. Physicists struggled to contain the implications. If voids actively erased light, then relativity's prohibition against faster-than-light processes might not be universal. Perhaps relativity was only a local truth, valid in well-behaved spacetime, but fractured in regions where the vacuum itself took on exotic forms. This idea unsettled even the most daring scientists. Relativity was more than a theory. It was the backbone of modern physics. To imagine it breaking, even locally, was to imagine an orderless cosmos. And yet, the data was relentless. Photons dimmed more quickly than expansion alone explained. Gravitational waves hinted at distortions not attributable to ordinary matter. Hydrogen vanished in defiance of formation models. Everywhere the voids were studied, they behaved less like deserts and more like anomalies, not passive gaps, but active agents of erasure. In the midst of this, new patterns emerged. The voids were not scattered randomly, but aligned with the cosmic web's geometry. They seemed to trace a rhythm, alternating with filaments of galaxies, like the negative spaces in a vast, unseen design. Some suggested that the universe itself was resonant, vibrating with patterns larger than galaxies, and that voids were the dark notes of its song. Others warned against metaphor, insisting on caution. Yet the imagery was hard to resist. The universe was not only structure and light, but silence and absence, and both carried equal weight in the cosmic balance. As investigations deepened, scientists began to suspect that the voids might be more fundamental than the galaxies themselves. Galaxies, after all, were transient, fragile structures born of gas and gravity. But voids vast, persistent, and strangely coherent might represent the true foundation of the universe. Perhaps reality was not built of matter within emptiness, but of emptiness punctuated by matter. Perhaps the voids were not interruptions, but the primary stage upon which all else played out. This realization carried an eerie implication. If voids were the foundation, then their strange behavior was not anomaly, but law. The universe then was not breaking its rules in the voids. The voids were the rules, and what those rules seemed to suggest was terrifying, that light, matter, even causality could be devoured, not as exceptions, but as features of the cosmic order. Philosophers of science began to weigh in. Was this the death of determinism, the end of laws as eternal truths? Or was it the beginning of a deeper order, one that transcended the language of relativity and quantum theory alike? The debate blurred the boundaries between science and metaphysics. For some, the voids became symbols of limits, the recognition that human comprehension could never fully grasp the universe. For others, they became promises, the first cracks in the wall that concealed the ultimate truth of reality. The investigation did not end, and likely never would. Each new instrument, each new map, peeled away another layer of silence, revealing not answers, but deeper questions. And yet, for all the confusion, a consensus began to form. The voids were not passive, they were active. They were not absences, they were presences. And in their presence, physics as humanity understood it trembled. Thus, the deeper investigations did not resolve the mystery. They only sharpened it. They revealed that the voids were larger, stranger, and more structured than emptiness should allow. They showed that light could falter, that gravitational waves could weaken, that hydrogen itself could vanish. They suggested that the foundation of reality was not certainty, but silence, a silence vast enough to swallow light, time, and understanding. And in that silence, one truth became clear. Science was not uncovering anomalies at the edge of physics. It was staring into the heart of physics itself, into the very fabric that allowed existence to be. And that fabric, against all expectation, was fraying. The voids should have been the end of the story. Statistical curiosities, perhaps unsettling, but ultimately folded into the grand narrative of cosmic structure. Yet as the 21st century advanced, the evidence refused to be tamed. Each new telescope, each new survey, deepened the silence. And what began as faint whispers of anomaly grew into something impossible to ignore. The voids were not fading under scrutiny. They were multiplying, spreading across the maps of the universe, and behaving in ways that defied every comfortable model. The first escalation came from scale. Voids were expected to exist, carved out by the expansion of the universe and the gravitational pull of galaxies clustering elsewhere. But the observed supervoids stretched to sizes that simulations declared improbable. Some spanned hundreds of millions of light years, yawning abysses where not a single galaxy shone. To call them empty was inadequate. They were too coherent, too sharply defined, their edges drawn as if by unseen hands. And within those edges, photons dimmed in defiance of fury. The second escalation came from time. As deep surveys reached further back into the early universe, voids appeared even in epochs when matter should have been nearly uniform. Their presence at such ancient times contradicted the slow, predictable growth of structure described by cosmological models. If voids already scarred the young universe, then something more fundamental than ordinary evolution was at work. They were not late-born accidents of clustering. They were primordial wounds. But the most chilling escalation was not scale or time. It was activity. In the cold mathematics of relativity, voids should be passive. They are places where matter is absent, where gravity is weak, where light travels largely unperturbed. Yet observations suggested the opposite. Photons crossing certain voids arrived with less energy than expected, as though drained during their journey. Cosmic microwave background measurements, tracing the imprint of ancient light, revealed imbalances where voids lay cold spots, sharper than chance allowed. Even gravitational waves rippling across the cosmos hinted at distortions, subtle shifts in their form when passing through these gulfs. The voids were not passive. They were active. They were doing something to the fabric of reality itself. For some, the explanation lay in dark energy, that mysterious pressure driving the acceleration of cosmic expansion. Perhaps voids were sites where dark energy pooled more strongly, stretching space-time faster than surrounding regions. If so, light might be redshifted into invisibility, photons drained of energy by expansion more violent than expected. Yet if this were the case, why were the boundaries so sharp? Why did the voids seem to carve the universe with precision rather than fade in gradients? Others turned to the unsettling possibility of vacuum instability. Quantum theory describes the vacuum not as nothingness, but as a sea of fluctuating fields. If our universe is vacuum, we're not truly stable, but only metastable, it might decay, forming bubbles of lower energy reality that expand at near the speed of light. Such a bubble, if it touched us, would erase everything, matter, energy, even the constants of nature without warning. Could voids be relics of such processes? Scars of bubbles that formed in the early universe and froze, silent reminders that reality itself can fail. The escalation was not only theoretical. Data itself seemed to throb with unease. Surveys found galaxies on the edges of voids brighter and more numerous than expected, as if the voids pushed matter outward, compressing the cosmic web into denser filaments. If voids were merely absences, why should they act with such force, shaping matter as though they had agency? The idea spread. Perhaps voids were not nothing at all, but something regions dominated by fields or energies still unknown. Their silence the mark of hidden presence. The terror lay not only in what voids were, but in what they implied. If vast regions of space-time could behave in ways relativity forbade, then the cosmos was not uniform. It was fractured. Its laws were not eternal and universal, but conditional, varying from one domain to another. This was not the smooth, elegant universe Einstein had envisioned. It was a patchwork, stitched together from rules that sometimes held and sometimes broke, a cosmos more unstable than comforting. For humanity, the escalation struck at a primal fear, the loss of permanence. We had long accepted that stars die, galaxies fade, even universes evolve. But we trusted that the laws, the equations themselves, would endure. The voids suggested otherwise. They whispered of domains where light faltered, where causality bent, where space-time itself might dissolve. If such domains could exist out there, what prevented them from appearing here? The philosophical tremor deepened. Some scientists began to speak of the voids as cosmic predators, not literally alive, but functioning with the same inevitability. Regions that consume, that erase, that spread. To look at the maps of the universe was to see not only the luminous web of galaxies, but the black eyes of these predators staring back. And still the escalation continued. As instruments sharpened, more anomalies appeared. Signals from pulsars, the ultra-precise lighthouses of the cosmos, flickered strangely when their beams passed near voids. Their timing shifted by nanoseconds, tiny but detectable, as though space-time itself had wavered. Fast radio bursts, mysterious millisecond flashes of energy from deep space, sometimes dimmed when aligned with voids, as if silenced mid-flight. These phenomena defied easy categorization, yet all pointed to the same conclusion. Voids were not inert. They interacted. They consumed. The community could no longer dismiss the anomalies as noise. The escalation was undeniable. What had begun as curiosities now loomed as one of the great mysteries of cosmology. If the voids were truly erasing light faster than physics allowed, then they were cracks in the foundation of reality. And in that realization, awe and fear mingled once again. Humanity had peered into the depths of the cosmos, expecting to find silence, and instead found a silence that acted. A silence that deepened with every observation. A silence that threatened to unravel the story of physics itself. The escalation pressed beyond astronomy into the very language of physics. Observations no longer whispered of anomalies. They shouted them. Every wavelength of the spectrum, radio, optical, X-ray, gamma, bore the scars of light erased too quickly, too completely. Every instrument pointed toward the same unsettling truth. The voids were not accidents of structure, not deserts carved by chance. They were active regions of space-time whose behavior threatened to dissolve the very principles on which physics had been built. Perhaps the most jarring escalation came through time-domain astronomy. This new field, born from the ability to scan the sky continuously, revealed that the universe is far from static. Stars flare, quasars flicker, galaxies collide, and now voids seem to join the chorus. Transient events, sudden disappearances of distant objects, were sometimes traced to lines of sight that intersected known voids. A quasar that should have remained steady dimmed abruptly. A fast radio burst, powerful enough to outshine galaxies for a moment, weakened as though swallowed mid-flight. The voids were no longer merely silent. They were dynamic, capable of interacting with events in real time. The fear this provoked was profound. If voids acted upon the present, then they were not fossils of the past, but processes of the now. They were not merely scars of cosmic history, but engines still operating, still consuming, still reshaping the universe. At conferences, the tension was palpable. Some physicists spoke in hushed tones of causality collapse, regions where time itself might not flow as expected. If photons could vanish faster than relativity allowed, then perhaps voids hosted domains where the speed of light was no longer the ultimate boundary. And if the speed of light failed, so too did the chronological order of the universe. In such regions, effect might precede cause, time might fold back upon itself, reality might cannibalize its own sequence. The language of fear began to merge with the language of speculation. Were voids embryonic horizons, proto-black holes on scales so vast that they defied classification? Or were they, as some dared to imagine, fractures between universes, rifts where our cosmos brushed against another realm of physics? Such speculations were whispered cautiously, but they grew louder as evidence piled higher. For what else could explain silence that was structured, consistent, and predatory? The escalation was not limited to ideas. It carried into the technological realm. As gravitational wave detectors increased in sensitivity, anomalies multiplied. Some signals arrived weaker than predicted, as if energy had bled away while crossing voids. Others carried phase distortions, subtle shifts in timing that hinted at space-time bending beyond Einstein's equations. These anomalies resisted easy explanation. They were not artifacts of noise. Their alignment with known voids was too consistent. The conclusion, unsettling as it was, pressed closer. Voids were not only swallowing photons, but perhaps bending the ripples of space-time itself. And then came the simulations. Supercomputers, armed with the best models of cosmic evolution, attempted to reproduce the distribution of galaxies, filaments, and voids. They succeeded. At first, small voids emerged naturally, just as expected. But when scaled upward, the simulations failed. They could not produce the vast supervoids mapped by surveys. They could not replicate the sharp boundaries or the depth of emptiness. The real universe, it seemed, was carving voids that theory could not. To many, this was the final escalation, the recognition that our simulations, rooted in relativity and dark matter cosmology, could not account for the universe we observed. The philosophical implications became unavoidable. If physics could not simulate the cosmos, then physics was incomplete. The voids stood as proof, written across billions of light years, that the laws humanity trusted were only approximations of a deeper, stranger order. For some, the fear turned existential. If voids were regions where physics faltered, then what prevented such a region from engulfing us? Could Earth one day be swept into a silence that erased light, causality, and matter, leaving no trace that we had ever existed? False vacuum decay models gave weight to such fears, describing bubbles of altered reality expanding invisibly at nearly the speed of light. Though no evidence confirmed that voids were such bubbles, the analogy was haunting. Humanity might live at the edge of an abyss, unaware until it arrived. And yet, amid the terror, awe remained. The voids, for all their menace, were also teachers. They revealed the limits of human understanding, the fragility of cherished theories, the vastness of questions yet to be asked. They reminded us that science does not exist to soothe, but to confront, to stare into silence and refuse to look away. The voids, in their hunger, forced humanity to admit its ignorance, and in that admission lay the possibility of growth. In the end, the escalation carried a strange poetry. The luminous filaments of galaxies, the shining islands of stars, had long drawn our attention. Yet it was the darkness between them, the silent gulfs, the swallowing voids, that revealed the truer strangeness of the universe. The cosmos was not only written in light, but in silence, and both were equally real, equally powerful. And so the chapter closed with a chilling recognition. The voids were not passive features of the cosmic map. They were active mysteries, spreading, multiplying, behaving in ways that threatened the coherence of physics itself. Their silence was not absence, but presence. A presence vast enough to consume light. A presence bold enough to challenge Einstein. A presence that whispered with quiet inevitability that the laws of reality may not endure forever. The mystery had deepened, and with it, the fear and the wonder of a universe unraveling before our eyes. The voids had escalated from curiosities into threats, from silences into presences. By now, the data was too consistent, the anomalies too persistent to be dismissed. If light itself could vanish more quickly than relativity allowed, if signals dimmed beyond natural models, then explanation was no longer optional. Science had to speculate carefully, reluctantly, but irresistibly. Theories multiplied, some grounded in familiar frameworks, others daring to reach into realms where mathematics trembled. The first path of speculation pointed, inevitably, back to Einstein. General relativity had carried physics further than any single theory in history. It predicted the bending of starlight during eclipses, the slowing of time in strong gravitational fields, the ripples of spacetime in colliding black holes. It had endured every test humanity had thrown at it, and yet the void seemed to lie beyond its reach. Could relativity be incomplete? Some physicists suggested that Einstein's equations, though elegant, might only describe spacetime under certain conditions. The well-behaved universe of stars, planets, and ordinary black holes. In the gulfs of the cosmic web, where matter was nearly absent and dark energy dominated, perhaps the rules shifted. Perhaps the speed of light was not absolute, but conditional, an emergent property of spacetime, rather than a fixed constant. In such a view, voids were laboratories where relativity cracked open, exposing the scaffolding beneath. Others turned to quantum field theory. To quantum physics, the vacuum is never empty. It teems with virtual particles, fluctuating fields, restless energies bubbling into existence and vanishing again. What if the voids were not empty deserts, but places where these quantum fluctuations behaved differently? Some speculated about vacuum decay, the possibility that our universe exists in a false vacuum state, a temporary condition rather than the true ground of reality. If so, voids might be the scars of decays, bubbles of altered vacuum that formed and froze. Within those bubbles, the constants of physics could shift, light could dissolve, causality could fail. The voids in this vision were not empty, but full of a different kind of reality. Dark energy provided another line of thought. Discovered at the close of the 20th century, it explained the accelerating expansion of the cosmos. But its nature remained unknown, a name for ignorance rather than a true description. If dark energy varied across space, pooling in some regions more strongly than others, perhaps voids were sites of its concentration. In those domains, space might stretch more violently, draining photons of energy, swallowing them into invisibility. Voids would then be the frontiers of cosmic acceleration, places where the future of expansion was already written. But dark energy alone could not explain the sharpness of the voids, their coherent boundaries, their strange alignment with anomalies in the cosmic microwave background. To some, this suggested deeper origins. Perhaps the voids were relics of cosmic inflation, the brief, violent surge of expansion that shaped the infant universe. If inflation had not been perfectly smooth, it might have left behind scars, bubbles where expansion ran differently, freezing domains of silence into the structure of the cosmos. In this view, voids were fossils, messages from the first fractions of a second after the Big Bang. Speculation grew bolder. The multiverse, once dismissed as philosophy, entered the conversation. If inflation spawned not one universe, but many, then collisions between domains might leave imprints. The cold spot in the microwave background, aligned with a massive void, looked suspiciously like such a scar. Could voids be places where our universe had brushed against another, their physics incompatible, their meeting recorded as silence? If so, then voids were not only anomalies, but boundaries, thresholds to realities beyond our own. Some theorists stretched further still, into the mathematics of tachyons and superluminal fields. Tachyons, hypothetical particles that always travel faster than light, had long been considered ghosts of equations rather than real entities. But could voids be domains where tachyonic fields dominated, erasing photons in their passage? In such regions, the very speed limit of the cosmos would fail, not as a violation, but as the normal order of things. Our physics, from that perspective, was provincial, true only to the regions outside the voids. And always in the background loomed Hawking's paradox. Black holes had already shown that relativity and quantum mechanics could not coexist without contradiction. Information could not both vanish, as relativity suggested, and be preserved, as quantum mechanics demanded. The voids seemed to echo that paradox on cosmic scales. If photons were erased, then where did their information go? Was it scattered into hidden dimensions, or lost forever? The voids, in this sense, were not merely cosmological structures. They were cosmic riddles about the fate of information itself. What unified all these speculations was not certainty, but desperation. Each theory grasped at fragments, each offered partial answers. None explained everything. Some models accounted for dimming, but not boundaries. Others explained boundaries, but not scale. Still others explained scale, but not alignment with the microwave background. The voids resisted total explanation, as if mocking the frameworks of physics. And yet, the speculation was necessary. To abandon it was to accept ignorance, to stare into silence without response. Theories, even fragile ones, gave shape to awe. They transformed fear into questions, and questions into research. They reminded humanity that even the deepest mysteries could be pursued, if not solved. Thus, the voids became more than anomalies. They became catalysts, forcing physics to stretch, to risk, to imagine. They became mirrors, reflecting not only the limits of the cosmos, but the limits of the human mind. And in their reflection, science glimpsed both terror and promise. The terror of a reality that could erase its own light, and the promise of a deeper order waiting to be discovered. As the voids pressed their silence upon science, speculation expanded into realms once considered fringe. Ideas that had lingered at the boundaries of physics but now found sudden urgency. If photons could vanish faster than physics allowed, then perhaps the voids were not only anomalies to be explained, but windows into the deepest architecture of the universe. String theory, long criticized for its abstraction, offered one of the most daring perspectives. According to its framework, particles are not point-like dots, but tiny, vibrating strings, their resonances giving rise to the forces and matter of the cosmos. Within this landscape, extra dimensions, hidden, curled up beyond perception, play a vital role. Some physicists wondered whether the voids might be domains where these hidden dimensions unfurl, altering the constants of physics and consuming light into geometries we cannot perceive. To us, it would look like erasure. To the universe, it would simply be a shift of pathways, photons bleeding into spaces unseen. The holographic principle provided another provocative lens. If reality is fundamentally two-dimensional, encoded on a cosmic boundary, then our experience of three dimensions is an emergent illusion. Black holes already hinted at this, their entropy tied not to volume, but to surface area. What if voids were vast demonstrations of the same principle? Perhaps they were regions where the holographic encoding falters, where information slips from the screen and cannot be recovered. Light would vanish not into darkness, but into the failure of the projection itself, a hole in the cosmic hologram. Some thinkers reached for emergent spacetime models, the idea that space and time themselves are not fundamental, but products of deeper networks of quantum entanglement. In this view, spacetime is woven from correlations, a tapestry stitched from information. If the fabric of entanglement thins or unravels, then spacetime dissolves. The voids under this interpretation could be regions where the entanglement web is weak, its threads too sparse to sustain reality. Light falters there because there is no stage upon which it can move. The silence is not erasure, but absence of the very medium that allows existence to be. Other speculations embraced a darker possibility, that voids were not natural at all, but consequences of cosmic censorship breaking down. General relativity usually protects us from naked singularities, places where infinities are exposed to the universe. But if voids were domains where censorship fails, then singular behavior might spread across millions of light years. They would not be black holes in the traditional sense, but singularities smeared across cosmic scales, swallowing light not by trapping it, but by denying the framework that allows it to exist. Such theories were dizzying, yet all circled back to a single recognition. The voids were not passive. They were telling us that our cherished constants, the speed of light, the coherence of causality, the persistence of spacetime, were not guarantees. They were conditions, fragile and conditional, that could fail under the universe's deeper rules. Philosophical questions emerged alongside the physics. If voids truly erased photons, what did that mean for information? Quantum mechanics insists that information cannot be destroyed, that every event leaves a trace. If voids obliterated information, then quantum theory itself fractured. But if information persisted in hidden dimensions, then our universe was larger and stranger than we could perceive. Either outcome was transformative. In one, physics was broken. In the other, physics was incomplete. The most unsettling speculations came from merging these threads. Imagine a universe where voids are expanding bubbles of new vacuum, erasing our laws as they spread. Imagine them as scars of collisions with other universes, boundaries where foreign physics intrudes. Imagine them as regions where space-time is not woven tightly enough, where the holographic code falters, where light falls into the cracks of the cosmic projection. Each vision was terrifying, yet each carried a strange beauty, the recognition that reality was not final, but alive, shifting, restless. Some philosophers of science suggested that voids represented a new category of mystery, not anomalies to be explained away, but revelations that demanded humility. Just as Copernicus displaced Earth from the center, and quantum theory displaced certainty from physics, so too might the voids displace light from its throne as the ultimate boundary. Perhaps they were teaching us that no constant, no law, no certainty was sacred. Perhaps the universe is not ruled by permanence, but by impermanence, a cosmos always on the edge of rewriting itself. In this way, speculation was not mere science fiction, it was necessity. It was the recognition that to face the voids, humanity must think beyond its frameworks, beyond the comfort of familiar equations. Theories, even fragile ones, offered footholds against the abyss. They gave form to silence, allowing awe to become inquiry, fear to become curiosity. The chapter of theories and speculations did not resolve the voids. It could not, but it transformed them from passive terrors into active challenges. They became more than gulfs of darkness. They became laboratories of imagination, canvases upon which science could project its boldest questions. Were they bubbles of new vacuum? Boundaries of other universes? Failures of the holographic code, or regions where space-time itself frayed into nothing? Each theory was provisional, each fragile. But together they carried a message. The voids are not the end of understanding. They are the beginning. They are invitations, asking us to confront a universe more fragile, more fluid, more astonishing than we have ever known. And in their silence, one truth lingered. The universe is stranger than light alone can reveal. To understand it, we must listen not only to what shines, but to what disappears. Not only to what speaks, but to what swallows speech. The voids are not absence, they are presence, a presence that forces us to imagine deeper laws, deeper realities, deeper truths than physics has yet conceived. In the face of silence so profound, humanity reached for sharper instruments. The voids, unsettling as they were, could not be dismissed as illusions. If they consumed light faster than physics allowed, then they were phenomena demanding relentless pursuit. The question was no longer if they existed, but how to study them, how to build tools capable of probing gulfs that seemed to resist observation itself. At the dawn of the 21st century, the universe became a laboratory on scales never before attempted. Telescopes, satellites, and detectors were no longer designed merely to collect light, but to interrogate reality itself, to test whether its most sacred laws held firm. Every photon became evidence, every ripple in space-time became a clue, and every silence became a data point in the greatest investigation of all. The Event Horizon Telescope marked a milestone in this pursuit. By linking observatories across the globe into a single Earth-sized dish, it delivered humanity's first direct image of a black hole shadow. Though its focus was the compact heart of Messier 87, its implications extended outward. If an array of instruments could capture the outline of an event horizon, might similar networks be tuned to probe the strange boundaries of cosmic voids? Researchers began to imagine global collaborations, not for single black holes, but for mapping silence itself, arrays designed to catch photons that slipped, dimmed, or vanished when crossing the Great Gulfs. Meanwhile, gravitational wave observatories like LIGO, Virgo, and CAGRA refined their sensitivity. What had begun as faint whispers of colliding black holes soon expanded into a symphony of cosmic events. Yet scientists began to ask whether these detectors might also catch distortions when waves passed through voids. If space-time itself was fraying, if gravitational ripples weakened in the silence, then detectors could reveal not only what had collided, but what the waves had crossed. The possibility of void signatures in gravitational wave data became a frontier of research, fragile, tentative, but electrifying. In orbit, satellites carried the investigation higher. The Planck satellite, though already retired, left behind exquisite maps of the cosmic microwave background, its cold spots still haunting debates. New missions were designed to surpass it: Lightbird in Japan, the Simons Observatory in Chile, the upcoming CMB-S4 experiment, each aimed to chart the faint polarization patterns of ancient light, to reveal whether voids had left their fingerprints on the earliest radiation of the cosmos. If the voids were scars of primordial processes, inflationary bubbles, multiverse collisions, or vacuum instabilities, then the microwave background might still echo their birth. The James Webb Space Telescope joined the effort from its perch at Lagrange Point 2. With its vast golden mirrors and infrared sensitivity, it peered deeper into cosmic time than any instrument before it. Webb's deep field images revealed galaxies shimmering in the first billion years of the universe, yet also revealed gulfs wider and stranger than expected. By charting the distribution of galaxies with unprecedented precision, Webb provided a new way to measure voids, not as absences of light, but as structured silences embedded in cosmic history. Particle physics, too, pressed into the mystery. The Large Hadron Collider had uncovered the Higgs boson, completing the Standard Model. But beyond that triumph, it hinted at instability. The Higgs field might not sit at the lowest possible energy state. If true, our universe could be metastable, perched precariously in a false vacuum. A collapse into a deeper state could rewrite the constants of nature in an instant, though no evidence confirmed such collapse. Theorists wondered whether the voids were linked regions where the vacuum was weaker, closer to decay, their silence the trembling of reality itself. Neutrino observatories added their weight. Deep underground, in ice and water, detectors like IceCube in Antarctica captured ghostly particles passing through the Earth. Unlike photons, neutrinos rarely interact with matter. They should cross voids untouched. Yet preliminary studies suggested faint anomalies, neutrino fluxes arriving weaker than expected when traveling across regions aligned with massive voids. If confirmed, such anomalies would be devastating. Or if even neutrinos near immune to the universe faltered in the silence, then the voids were not erasing light alone. They were touching every fundamental messenger of physics. The square-kilometer array, spread across South Africa and Australia, promised yet another window, designed to map the faint whispers of neutral hydrogen across cosmic history. It would trace the skeleton of the universe with unmatched clarity. Hydrogen was the raw fuel of stars, the ink with which galaxies wrote themselves across the sky. If voids truly stripped it away, the SKA would reveal the scars, its maps stretching billions of years into the past, could determine whether the voids were accidents of evolution or if they had been inscribed into the cosmos from the beginning. And yet, for all the instruments, the challenge was profound. How does one measure silence? How does one test the absence of light? Scientists learned to invert their thinking. Absence was itself a signal, silence a form of data. The failure of photons to arrive, the dimming of quasars, the thinning of hydrogen, these became as meaningful as explosions and collisions. Every missing photon was a message. Every vanished particle was a clue. Ongoing tests became global collaborations, weaving together astronomy, cosmology, and particle physics. It was not enough to stare at voids with a single instrument. Only by combining data across wavelengths, across particles, across messengers, could the truth be approached. This multi-messenger astronomy became the guiding principle. Photons, neutrinos, cosmic rays, gravitational waves, all united in pursuit of the silence. The tools were powerful, but what they revealed was humbling. With every new test, the voids grew stranger. They resisted easy classification, mocking attempts at neat theory. Each anomaly confirmed the same truth. The voids were not illusions. They were real, structured, persistent, and active. And their silence, far from receding, deepened under scrutiny. The investigations were not only technical, but existential. Each new experiment sharpened the question. If voids consumed light faster than physics allowed, what did that mean for the laws we trusted? What did it mean for humanity to live in a universe whose foundations could falter? The answer remained elusive, but the pursuit itself, the relentless building of tools, the ongoing testing of silence, became humanity's reply. If the voids whispered of collapse, then humanity would answer with instruments, with data, with the determination to stare into the abyss and measure even its silence. The quest to confront the voids did not pause with the tools already in use. Science is restless by nature, always building the next instrument, always preparing to see further, to measure more finely, to test reality with greater precision. If the voids were real presences consuming photons, warping gravitational waves, dimming even neutrinos, then future observatories would need to face them directly, with technologies designed not only to look at light, but to interrogate silence itself. One of the most ambitious ventures lies in the Vera C. Rubin Observatory, with its Legacy Survey of Space and Time, LSST. Over a decade, it will capture the entire sky every few nights, compiling a cosmic film of billions of galaxies. For the first time, humanity will not only map where galaxies are, but how they shift, shimmer, and vanish across time. If voids erase light actively, Rubin's survey may record the disappearances, quasars dimming, galaxies fading, not as static absences, but as evolving events. Its data will offer the most detailed census of cosmic voids ever attempted. The Euclid mission, launched by the European Space Agency, complements this effort. By mapping dark energy and dark matter through weak gravitational lensing, Euclid will trace the scaffolding of the cosmic web. If voids warped spacetime beyond Einstein's predictions, Euclid's precision may reveal distortions too sharp, too extreme to be explained by standard models. In its maps, silence itself may leave its fingerprint. Further ahead, the proposed Nancy Grace Roman Space Telescope promises to deepen these tests. With a wide field of view and the ability to probe dark energy through supernovae and baryon acoustic oscillations, it may reveal whether voids are simply exaggerated features of cosmic expansion, or whether they demand a new law of physics altogether. the search extends beyond photons. Gravitational wave astronomy is preparing for its next leap. The Laser Interferometer Space Antenna, LISA, a trio of satellites flying millions of kilometers apart, will listen to space-time ripples on lower frequencies than Earth-based detectors can reach. These long waves, produced by supermassive black holes and cosmic strings, may pass through voids with greater vulnerability. If their shapes bend, if their strength fades, then LISA may become the first observatory to chart voids not by light, but by gravity itself. Cosmic ray detectors join the effort as well. High-energy particles strike Earth constantly, accelerated by violent events across the universe. Yet their paths are deflected by magnetic fields, scrambled into near randomness. Still, if patterns of suppression align with cosmic voids, they may reveal that even the most energetic particles falter in those gulfs. Experiments such as the Pierre Auger Observatory continue to test this. Their vast arrays of detectors, listening for whispers in the rain of cosmic fire beneath the Earth. Particle physicists are not idle. Plans for next-generation colliders, such as the Future Circular Collider in Europe or China's proposed CEPC, aim to probe energies far beyond the Higgs boson. These machines may reveal whether the Higgs field, the field that gives particles mass, is stable or precarious. If it proves unstable, then voids could be its expression, domains where the vacuum trembles, closer to collapse. Such experiments may reveal not only why voids consume light, but whether the universe itself balances on the edge of failure. Meanwhile, neutrino astronomy is preparing its renaissance. IceCube's successor, the planned IceCube Gen 2, will expand its detectors deep into Antarctic ice, capturing far more neutrinos from far greater distances. If the faint anomalies already suggested are real, IceCube Gen 2 may confirm whether voids dim even these ghostly messengers. Should the answer be yes, then no signal, not photons, not waves, not neutrinos, will be safe from erasure. The future also lies in multi-messenger synergy. No single instrument can confront the voids alone, but together, photons, neutrinos, gravitational waves, cosmic rays, they may weave a portrait of silence. Already, coordinated campaigns between LIGO, IceCube, and high-energy telescopes have shown the power of unity. Tomorrow's collaborations will turn that unity upon the voids, asking whether silence can be triangulated, measured, and described as rigorously as light itself. Yet, even as the tools sharpen, scientists remain haunted by a question. What if the voids resist all observation? What if their nature is not to reveal, but to erase? Instruments may grow stronger, but perhaps the voids erase not only light, but meaning, not only photons, but comprehension. Could humanity spend centuries building sharper eyes, only to find the silence growing deeper? Still, the pursuit itself matters. Each telescope, each collider, each detector is an answer to despair, a refusal to accept that the voids are unknowable. In the act of measuring silence, humanity affirms that even if the voids consume, they will not consume curiosity. The building of tools becomes a defiance, a declaration that no mystery is too vast, no silence too deep to chase. And so the chapter of ongoing testing continues, not as closure, but as promise. With every new mission, the voids grow stranger. With every new instrument, they loom larger. The more science probes, the more the abyss seems to expand. But within that expansion lies the essence of progress. For in the end, the voids may never yield fully to understanding. They may always remain partly beyond reach, presences too vast for equations, too subtle for instruments. But by chasing them, humanity learns more than facts. It learns humility. It learns perseverance. It learns that knowledge is not a final state, but a pursuit without end. The voids consume light, but in their consuming, they illuminate the most human truth of all, that we are creatures who refuse to stop asking, even when the universe itself whispers that answers may not exist. The silence of the voids was more than a puzzle for equations. It was a weight pressing upon the imagination of humanity. For centuries, science had expanded the boundaries of the known, replacing mystery with order, turning superstition into understanding. Yet here, at the edge of comprehension, the voids whispered not of mastery, but of fragility. They forced the question that lay beyond mathematics. What does it mean for us to live in a universe where even light itself can be erased? At its heart, the human question was about permanence. Civilizations are built upon the assumption that the world is stable, that the sun will rise, that the stars will shine, that the laws of nature will endure. Even mortality finds meaning against the backdrop of permanence. Though lives end, the cosmos continues, but the voids challenged that comfort. They suggested that even the constants of reality, the speed of light, the coherence of causality, the persistence of spacetime, may be temporary. They asked whether permanence itself is an illusion. Philosophers wrestled with this as keenly as physicists. If the voids revealed domains where reality dissolved, then perhaps the universe was not a coherent whole, but a patchwork, stitched together from rules that could fray. To some, this was terrifying. It meant that no principle, no equation, no truth was absolute. To others, it was liberating. It meant that reality was alive, evolving, unfixed, full of possibilities yet unseen. For ordinary people, the voids became metaphors as much as mysteries. They entered art, literature, and poetry as symbols of loss and erasure. To look at an image of the cold spot or to hear of a supervoid spanning 500 million light-years was to confront a silence that resonated with human fears of absence. The voids became mirrors of grief, reflections of the fragility not only of stars, but of memory, identity, and meaning. If light itself could vanish, what hope was there for the stories we tell, the lives we live? Religious thinkers, too, found themselves drawn into the debate. Some saw in the voids evidence of the limits of science, a reminder that not everything could be measured. Others saw them as proof of creation's mystery, gaps through which the divine might still speak. The voids, like black holes before them, became sites where science and spirituality overlapped, both gazing into the same silence and asking what lay beyond. For scientists themselves, the human question was more intimate. To dedicate a life to equations, to telescopes, to experiments, is to believe that the universe is intelligible. The voids threatened that belief. They whispered that intelligence may not be enough, that curiosity may never reach its goal. Was the pursuit of knowledge still meaningful if some mysteries could never be solved? Or was the pursuit itself the meaning, regardless of its end? Psychologically, the voids awakened an ancient fear, the fear of nothingness. Humans have always filled silence with story, darkness with fire, absence with gods. To confront voids that may truly erase not only light but causality, not only photons but laws, was to stare into a nothingness deeper than imagination. It was to feel that the universe itself might one day forget us, not with malice, but with indifference. Yet paradoxically, in this fear lay awe. The voids reminded humanity of its smallness, but also of its courage. To look into silence and still ask questions, to stare into erasure and still measure, to admit ignorance and still pursue this was not weakness, but strength. It was the essence of being human. In classrooms, students looked at images of the cosmic web, bright filaments of galaxies against oceans of black, and asked whether the darkness mattered as much as the light. In laboratories, researchers wrote equations that faltered at the edge of voids, and still they wrote more. In observatories, astronomers pointed mirrors at gulfs that gave nothing back, and still they stared. The human question then was not only what are the voids, but what are we in their presence? Are we fragile sparks destined to be erased? Or are we beings defined not by permanence, but by persistence, by the refusal to stop asking even when the universe answers with silence? The voids swallowed light, but they also illuminated humanity. They showed that science is not about final answers, but about the courage to face the unknown. They revealed that meaning does not come from certainty, but from the act of seeking. They whispered that even if reality itself is unstable, even if the laws themselves can falter, the human spirit endures in its curiosity. And so, the voids became more than anomalies. They became parables not of despair, but of humility and wonder. They reminded humanity that existence is fragile, that knowledge is provisional, that meaning is not found in permanence, but in pursuit. If the voids revealed anything beyond physics, it was the vulnerability of certainty. Humanity had long believed that by uncovering the laws of the cosmos, it was drawing closer to permanence, closer to an ultimate truth that could not be broken. The voids unsettled this belief. They suggested that truth itself may be conditional, that what we call laws are not eternal decrees, but temporary agreements of reality, prone to fracture. This realization carried existential weight, for if the universe could change its rules, then permanence was an illusion, not only in life, but in physics itself. What then was the place of humanity in such a shifting cosmos? Were we fragile accidents, destined to vanish without memory? Or were we, in our curiosity, participants in the great unfolding, not authors of truth, but witnesses to its fluidity? The voids posed a challenge to meaning. If reality itself can erase light, can dissolve causality, then how should human beings anchor their sense of purpose? Some responded with despair. If even physics can vanish, then nothing endures. Others responded with wonder. If even physics can shift, then meaning is not given but made, woven not from permanence, but from persistence. In this view, humanity's role was not to cling to certainty, but to live in the courage of uncertainty. The cultural echoes of this realization spread widely. Writers spoke of the voids as metaphors for memory lost, for histories erased, for civilizations forgotten. Painters evoked them as vast dark canvases swallowing the strokes of color. Musicians translated their silence into minor chords, unresolved progressions that left listeners suspended. The voids became symbols not only of absence, but of the fragility of all things we hold dear. And yet, paradoxically, this fragility deepened value. If the universe could forget, then every act of remembering became sacred. If light could vanish, then every flicker mattered. The voids, by threatening to erase, sharpened the meaning of what exists. They whispered that significance does not come from eternity, but from the fleeting brilliance of being, however temporary. For scientists, the human question narrowed to humility. To peer into the cosmos is to expect answers. But the voids offered resistance. They reminded science that knowledge is provisional, that theories are scaffolding rather than temples. And in this reminder lay a gift, the recognition that ignorance is not failure, but opportunity. The voids forced physicists to admit not only what they did not know, but what they might never know, and to find dignity in the pursuit nonetheless. For philosophers, the voids reopened questions as old as thought itself. If reality is unstable, what is truth? If causality can falter, what is time? If information can be erased, what is memory? The answers varied, but the process of asking revealed something profound, that philosophy and science, often divided, converged at the edge of silence. Both sought meaning in absence. Both stared into gulfs too vast to comprehend. Both admitted their limits, and yet both persisted. Religious and spiritual traditions, too, absorbed the message. Some saw in the voids an affirmation that the universe is more mysterious than human comprehension, that mystery itself is sacred. Others saw them as warnings, reminders that no creation is eternal, that all things, stars, galaxies, even laws, may pass. The voids became, in their way, sermons of humility, asking humanity to let go of pride and embrace awe. And for ordinary people, those far from telescopes and equations, the voids became stories. Stories of silence deeper than darkness. Stories of light swallowed by absence. Stories that reminded them of mortality, of fragility, of the strange beauty of impermanence. The voids entered human imagination, not only as science, but as myth, symbols of both terror and transcendence. The deepest human question, however, lay beyond culture, philosophy, or science. It lay in reflection. What if reality itself is fragile? What if the constants that cradle us, gravity, light, time, are not eternal but contingent? Would we still live as though permanence mattered? Would we still create, love, and remember? Or would we live differently, knowing that even the laws of the cosmos might someday dissolve? The answer, perhaps, is that we would live much the same, for humanity has always lived under impermanence. Stars die, civilizations fall, lives fade, and yet, in the face of loss, we create meaning. We write books, paint images, compose music, build monuments, raise children, and dream. If the voids teach anything, it is that fragility does not erase meaning. Fragility is meaning. The fleeting is precious, precisely because it does not endure. Thus, the human question does not end in despair. It ends in defiance. The voids may erase photons, may consume causality, may silence signals across billions of years, but they cannot erase the act of asking. They cannot erase the courage to seek. They cannot erase the human refusal to turn away from silence. And so, humanity stands in a universe where light can vanish faster than physics allows, and still it gazes upward. Still it builds telescopes. Still it writes equations. Still it tells stories of stars and silence. The voids may consume, but they also inspire. They remind us that meaning does not come from certainty, but from wonder, from the endless, fragile, beautiful act of asking questions in the dark.